We tend to think of the lipids in our body as fuel waiting to be burned, but cholesterol is entirely non-caloric. The human body has absolutely zero enzymatic pathways to break its carbon bonds for energy. You cannot burn it. Instead, it operates as a permanent structural asset. Its tetracyclic ring system is virtually indestructible, and 90% of your supply sits right here, packed into your cell membranes to maintain their physical integrity. Because it's critical for survival, every nucleated cell in your body comes equipped with a 30-step internal assembly line to build cholesterol from scratch. But running that factory comes with a punishingly high price tag. This diagram tracks the pathway's chemical expense. Constructing just one cholesterol molecule costs 18 ATP and 16 NADPH. But factor in the energy those raw materials would have provided if burned for fuel instead, and the true cost exceeds 100 ATP equivalents. Cells cannot destroy this molecule, and they can barely afford to make it. This biological reality forces the human body into a delicate, continuous balancing act of systemic import and targeted export to stay alive. To avoid paying massive internal manufacturing costs, your cells rely on a highly sensitive internal thermostat. This gauge represents the endoplasmic reticulum. Here, SREBP2 monitors local cholesterol concentration. It sits idle until the level drops to exactly 5 mol%. Then, a mechanical switch flips, triggering an emergency response to acquire sterols from the outside world. Rather than firing up its own expensive 30-step factory, the cell prioritizes building specialized receptors and pushing them to its surface, hoping to catch cholesterol that is already circulating in the bloodstream. The liver supplies that circulating pool. It acts as a central shipping hub, packaging cholesterol into dense delivery vehicles that progressively strip away their fat content until they become pure cholesterol-rich alveolar particles. Those LDL particles travel the circulatory system as a mobile reservoir of structural material, waiting to be pulled in by any peripheral cell that signals a deficit. Circulating LDL acts as a massive energy conservation system. It allows highly active tissues to immediately grab the structural components they need without draining their local ATP reserves. There is, however, one major organ entirely cut off from this logistical supply chain. The blood-brain barrier is a dense vascular wall that completely blocks systemic lipoproteins from entering. The brain must operate in isolated self-sufficiency. Despite this isolation, the central nervous system holds a quarter of your total body cholesterol. Every single molecule is synthesized locally by specialized support cells called astrocytes, which then distribute it to your neurons. For the rest of the body, the primary challenge is not isolation, but accumulation. Since peripheral cells cannot break down the sterol ring, any excess cholesterol risks building up inside the cell's mitochondria, impairing function and causing oxidative stress. To clear this hazard, the body uses reverse cholesterol transport. High-density lipoproteins, or HDL, act as an active cleanup crew, pulling unneeded sterols directly out of peripheral tissues. HDL carries that excess cargo safely back to the liver. Because the liver is the only organ equipped with the enzymes necessary to convert cholesterol into bile acids, it serves as the single functional exit door for the entire system. This obligatory disposal route offsets the constant cellular import. Maintaining healthy tissues requires a strict cycle of systemic delivery, careful cellular reuse, and controlled hepatic excretion. Because we recycle so effectively, human cholesterol turnover is incredibly low. We cycle through only about 0.7% of our total pool per day. That efficiency makes our vascular system highly sensitive to logistical bottlenecks. When the liver fails to clear LDL particles from the blood fast enough, they become trapped inside the arterial walls. This kicks off a pathological accumulation of atherogenic material that eventually hardens and restricts blood flow. This split-screen diagram highlights the two primary ways a patient's system gets overloaded. On the left, we have hypersynthesizers, whose internal factories constantly overproduce cholesterol. On the right are hyperabsorbers, whose intestinal tracts pull an excessive amount of dietary and biliary sterols back into the bloodstream. Recognizing this difference dictates precision medicine. Statins work by efficiently shutting down the internal synthesis factory on the left, while a drug called ezetimibe blocks the overactive intestinal absorption gates on the right. For severe bottlenecks, doctors use PCSK9 inhibitors. These drugs block the specific protein that normally degrades LDL receptors. By keeping those receptors active on the cell surface, the liver is forced to continuously pull massive amounts of excess LDL out of circulation. Mastering the human cholesterol economy means identifying exactly where the supply chain breaks down. By overriding these specific logistical bottlenecks, we turn a rigid, potentially fatal structural asset into a system we can directly control.